For number 33, we do have to find the approximate x coordinates of the points of intersection of the given curves. Now, we do have to use a graphing calculator on this one, and as we can see, the symbol over here indicates that, just because it would be very difficult for us to draw the function x times sine of x squared. So let us go to our graphing calculator. That is not what I meant to do. Let's see. So for our graphing calculator, I do like using Desmos, and I have plugged that in. So the one in red is the function x times sine of x squared, and the one in blue is y is equal to x to the power of 4. So we can see that the area between them is actually over here, and that the upper curve is the red curve, so x times sine x squared, and the lower curve is x to the power of 4. And that their points of intersection, it does go from 0, right? This is the point where they intersect, all the way to 0.896 on the x-axis. So let us set up our integral. This is the integral from 0 to 0. What was that? Was 896, yes. 0.896, and then the upper curve is x times sine x squared, and then the lower curve was minus x to the power of 4, and all of this times dx. So what I'm going to do is I am going to break this to use a u-substitution, right? So I'm going to say that u is equal to x squared, and then du is equal to 2x dx, and therefore du divided by 2 is equal to x dx. So let us just change this integral a little bit so that we can make this substitution. So what I'm going to do is I'm going to factor out the x, just so that I have x dx outside, and then I can easily substitute. So this is the integral from 0 to 0.896 of sine of x squared, and then minus x cubed, because I'm factoring out an x, right? And then times x dx outside. So let us substitute things in. So now for this x cubed, it might be a little difficult to substitute, right? Because we do have x times x squared, but it's just, we can also write this down that if we take the square here, if we take the square root of both sides, we just have square root of u is equal to x. So we can also just do the substitution. So let us plug things in. So this is the integral from 0 to 0.896 of sine of u minus, so x cubed is x squared times x, right? So this is just u times square root of u, and then all of this times du, and then we do have to du over 2. So let us just clean this up a little bit, and then we can integrate. So this is the integral from 0 to 0.896 of, and I'm going to bring the 1/2 to the outside, and that is sine of u minus u to the 3/2, and then all of this times du. So we're ready to integrate. This is just equal to 1/2 times the integral of sine of u is just minus cosine of u, and then this integral is minus u to the 5/2 times 2 over 5, evaluated from 0 to 0.896. And now let us just substitute it back. So we do have that this is equal to, and I'll just apply the 1/2, I'll just multiply that out now. So I have minus cosine of x squared divided by 2, and then this is equal to minus x squared times 5 over 2. So the 2's cancel out because when we multiply this, this is just x to the power of 5. So let's rewrite this. This is just x to the power of 5. The 1/2, when we multiply this over here, it will cancel out. So this just gives us minus x to the power of 5 over 5. And all of this from 0 to 0.896. So all we have to do now is plug this in our calculator. So let's see, 0.896, when we square this, we have 0.8028, and then when we take the cosine of this, divided by -2, we do have, this is minus 0.347, and then minus 0.896 to the power of 5 divided by 5, 0.896 to the power of 5 divided by 5, so minus 0.115. And then we're going to go minus cosine of 0 divided by 2. Cosine of 0 is just 1, so plus 1/2, right? Because that is 1 divided by 2, 1/2, and then minus. And then minus 0 to the power of 5, so which is just 0. So when we work out this math, let's see what that gives us. Plus 0.5 minus 0.347. So this is, and I will actually put the approximate symbol. This is approximately 0.038. So yes, that is approximately the area between these two curves. As we can see, it's almost, it's a very small area, right? As we saw here, we had to zoom in pretty far, so it seems accurate.